So representing ions, for anions, it's very easy, all right? A negative ion is formed by the addition of electrons to the p subshell until it is full. So we simply have to have enough electrons available to fill the p orbitals. And that's what determines the charge. So we've got nitride ion, a nitrogen atom that has gained 3 electrons, it becomes the nitride ion. And that the reason it's stable with 3 electrons being added is because that's what is needed in order to fill that p subshell. All right. So let's just, I'm going to do both energy level diagrams, and I'm going to do electron configuration. So energy level diagrams and electron configuration. And last day I finished off by talking about a shorter way of doing it. We called it the core energy level diagrams, or the core electron configuration. So we're going to start back with this diagram to the previous noble gas, which really isn't much. It's just helium, but that's kind of the standard way we do things. So helium is our core, all right? And then as we continue forward from helium, we are in the second row and we're in the s block. So the 2s orbital is what's being filled next. So 2s, and then as we move along, we are then filling the 2p orbital, all right? And in the regular energy level diagram for nitrogen, we have 2 electrons in the 2s. So here we're really talking about our valence electrons, right? When we do a core energy level diagram or a core electron configuration, we're not worried about those inner electrons. We're only worried about the valence electrons. So now I'm going back to what we learned when we were talking about Lewis diagrams years ago. Nitrogen will have 5 electrons in its outer shell. This energy level diagram, this core energy level diagram, only deals with the outer shell, which means I'm going to have 5 electrons in it. 1, 2, 3, 4, 5. Whoops, 5. All right? So there is regular nitrogen. In order to create a stable ion, we fill the p subshell until it's full, which means in this case, we need 3 electrons. 1, 2, 3. You don't have to put them in a different color. It's not a big deal. But you'll notice we added 3 electrons, and therefore the charge on a stable nitrogen ion or nitride ion is -3. Okay? So we simply fill it until we get to the nearest noble gas. That's what we did before when we were creating nitrogen or nitride ions using Lewis diagrams. We would have did something like this: 1, 2, 3, 4, 5. We would have added 3 electrons, and we would have had then something like this: 3 minus. And here we're doing it in terms of our energy levels, in terms of our s and p orbitals. All right? In terms of the electron configuration, again, we're going to start with the core. And our 2s is full, 2s2. And our 2p normally has 3, but in this case, because it's full, it has 6. All right? So this is the nitride ion. All right? I guess you could write this down. Because it is right full, it now looks like argon. All right? So the nitride ion looks like argon, because we've filled that p subshell. Yep. What did I do? Yes. It would be neon. It means that I looked over there too quickly and didn't actually get a look at, what was I looking at? I saw an N in here. No, neon. Correct. Very good. Thank you. Yep. I would rather you write it out as being 2s2 and 2p6. I was making more of a point that it's the same as that. I guess if you did it and you were in a hurry, I wouldn't Yeah, I probably wouldn't ding you, but I'd rather it be written so I could see that it's been filled. Yeah. Okay. I'm going to clear the slide so that we can do the selenium -2. All right. Now, neon was, yeah, I'm going to just clear the screen so we can do that one. I was going to, so I'm going to do a clear screen. Is everybody okay? We've got all that information. So let's just clear the screen, clear ink. So again, now I'm going to look at the selenium. Looking over at that one, where are we? SE. So we're going to go back to the energy level diagram. It's going to be argon in this case. Again, continuing on, and go ahead if you're understanding this. I hope you do. So if we're starting at argon, then the next one we're going to fill is the 4s. So down here, I'm going to have 4s, and it's going to be filled. The next thing we fill is which d orbital is this? What do we call this one? What's the letter designation for this guy here in the middle here? What's it going to be? Yep. It's a 3d. So I'm going to put it over here because I like to put the p in the middle. So 1, 2, 3, 4, 5. And that's going to be full. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As they fill, it always fills half first, and then we go back. But because we know it's full, I just loaded that right up. And that is 3D. And now, because I like to put the P in this position here, back to the 4P. And if we look at selenium, it's in group 16. It's 4 into the P subshell. I'm going to have 4 of those. 1, 2, 3, 4. And in order for it to become stable, we need to fill the P subshell. And so I'm going to add 2 more. And that gets me my -2 charge. All right? If we're doing the electron configuration for this, and I know I'm a little tight on space here, you guys can spread it out nicely, but I'll just kind of do it up here in this space here, the electron configuration. Again, back to argon, AR. Working my way across, 4s2, 4s2, 3d10. Under normal conditions for just a selenium atom, it would be 4p4, but because we've got a -2 charge, it is 4p6. So in order to make that anion, that negative ion, you're simply loading the p orbital full. All right? Okay? Go ahead. Cations are a little more difficult. Some of them are pretty straightforward, but others take a little extra thought to explain. So for the negative ions, it's easy. Fill the p orbital up. You've got it. You've got a stable anion. For the cations, we're removing electrons, and they can be removed from S, P, or D subshells. So we have to look a little more critically at the electron configuration or energy level diagram. It doesn't matter which one you're thinking in terms of. You have to look a little more critically in order to explain the charges on those ions. A positive ion is formed by removing electrons from S, P, or D sublevels. Electrons are removed from the sublevels with the highest principal quantum number, all right? So that means the biggest number in the letter designation, the 4 of the 4s, right, or 3 of the 3s. So the highest principal quantum number, we remove them from first. And then the highest energy subshell or sublevel. So this second little bullet, this one basically says we're removing the ones from the biggest number first, biggest number, right? And here the highest energy. So we remove from goodness gracious. D subshells have higher energy than P subshells, then F subshells, so we remove from D's first and then P's and then F's, right? So D's first, D first, right? Then P, then S, all right, depending on what you've got there. A stable cation is one in which all the electrons have been removed from a particular sublevel. So we either take them away from all the D's and then all the P's and then all the S's. I got to be careful in here. There might be a little reversal in there. Anyway, a stable cation is not necessarily isoelectronic to the nearest noble gas. So we are now to the point where we're not necessarily taking all the electrons away. All right? When we talked about ions in the past, we only talked about group 1 and group 2. And we talked about removing all of the electrons until they became the same as the previous noble gas. That is not the case anymore. We take electrons away until we've got empty sublevels, and then that will explain them. And I got to be careful. We don't necessarily take them from the D first, because that P is of higher energy, and then the D. I want you to cross this out. I'm not a fan of that right there. If you've got that written down, I want you to take that out. I've made an error on that, I think. Let's look at some examples. I think the P is thought of as having the higher energy because it is higher up on the side. Let's go through some examples here, and I'm going to take some room. I'm going to take the entire slide for each example. So I'm just going to do the aluminum +3 now first, and then I'll clear the slide and we'll move on from there. So in the past, did you have a question, Catherine? Yeah. Yeah, you do. You do. Yeah. And I got myself mixed up there by that little line. That's exactly correct. Okay. So let's start with, let's just do this with electron configuration, so we're not drawing all these shapes and all this other stuff. And they do mean the same thing. It just means we don't have to do quite as much drawing. So let's start by drawing just the aluminum atom itself, no charge. And so if I draw the aluminum, and hopefully you can already do this, we're starting with the neon, 3s, et cetera, et cetera. So we're starting with neon, and it is 3s2, and then it is 3p1. 3p1. Have I got that right? I'm second guessing myself all of a sudden because of this D thing, but it does work out. I don't know what I'm tripping over here for some reason. So if I want to cause an aluminum +3, because we know that that's the most stable, that is really the only stable ion, we've got a +3 oxidation state. You can see here that I'm going to remove first from this P, because it's of higher energy, it gets filled last. Then I'm going to remove from this S, and in this case I have to remove 3, so all 3 of these will be gone, and so in aluminum's case, it does become isoelectronic to neon. Now that's not always the case, but it is in the case of aluminum this time. All right? I think I have enough room now to just do, I'll keep going with the SB. So SB0, let's do that as first so we can compare it. Antimony, right down here. Previous is krypton. Then working my way across, 5, right? 5s2, 5s2, and then 3d10. I am totally screwed up. 4d10, 4d10, and where am I at here? 1, 2, 3, 5p, 5p3. Okay. According to the rules, I'm going to remove from the highest energy levels first, which means I'm going to be removing from the 5s before I remove from the 4s. That's why on the periodic table, what they do is they always order the lowest numbers and they put them first. So if you take a look at your periodic table and you look at the electron configuration on your table, they will have the 5s at the end and the 4 near the beginning. Is that correct? That's the way it looks? And that's because in creating a stable ion, you always take it from the 5s first. Okay? And so then when you're creating your ions, you don't have to worry about what this number is, because you're simply going to be plucking them off the back as you go. Now, my little statement about the D's before the P's is a true statement, but we don't have to worry about it because I've got to deal with this 5 and this 5 first. And then it goes P and S. We really don't have to think about the D, but the P will always come off first before the S. So if I'm going to make antimony +3, which electrons are removed in this procedure? Yep. The 3 P's. They're the highest energy level, and then they're the highest energy sublevel. So if I make a +3, I need to remove those. All right? 4d10, 5s2. Now, if we take a look at antimony, antimony can have -3, +3, and +5. To have +5, you can see here that we can also remove 2 electrons from the S. So to get +5, we remove the 3 from the P, and then the 2 from the S, and you have 4d10. That's it. Okay? This theory successfully explains why we have multivalent metals, metals with more than one oxidation state. I didn't do this in this case, but there's an anion for antimony. It can also have a -3 charge, and you can see here we could add 3 electrons to this p orbital and make it a 5p6, and that would make it a negative ion. All right? So this essentially allows us to explain these different oxidation states. I'm going to clear, and then we'll look at the nickel one. So let's, what did I do here? I don't want that. I want this one. Clear, clear, push on the button. Clear ink. So let's look at nickel. So I'm going to start with Ni0. Always easiest to just kind of look at what the original one is. So nickel, here we are in the middle of our transition metals. We've never really looked at the configurations for the transition metals before. We've never done Lewis diagrams for them. So let's go ahead and just follow it. We're going back to argon again. Argon. And then I'm in row 4, 4s2. And then I'm 5. That's a terrible 5. That's not supposed to be a 5. It's a 3. Whoa! No eraser. I'm clearing. I'm clearing the screen. You guys keep going without me. Ni0. What did we say it was? Argon? Argon and 4s2 and 3d, how many? 8? 3d8? 3d8. And now we want to look at the nickel plus 2 charge. Nickel plus 2. Nickel plus 2. Now I didn't do it this time, but notice on your table, it'd be flipped. Where are the 2 electrons going to be removed from? Ben? The 4s2. If we had it flipped, it would be the one on the end. So nickel plus 2 is the same as argon, and then 3d8. All right? That's what it is. The D subshell is partially filled, but it doesn't affect that charge. We take the electrons from that 2s, so it's these 2 that are leaving, and that's why we have a nickel plus 2. All right? Yep. Sure you could. Sure you could. Yeah, you would just take one out of there. Yep. So here we've got nickel plus 3, argon, would now be 3d7. We would take one out of there. And that doesn't have any inherent stability any better than the other one. Again, the D subshells can be partially filled. They can be partially filled, and it doesn't affect that very much. So yeah, you can have a plus 3. You might say, why can't we have then a plus 4 and just have a 3d6? There's just something not inherently stable about that. It just doesn't exist. But that would be the electron configuration for the plus 3. Okay? Yep. You can have partially filled Fs as well, but you wouldn't have stable ions with partially filled p orbitals. Is there an explanation for it? Do I have an explanation for it? Not a satisfactory one, really. There would be an explanation for it. It would have to do with the energy values of the d orbitals being so close together, and it's not a good explanation at this point, but the d subshells can be partially filled. Yeah. Okay. Let's now talk about some anomalous electron configurations. Anomalous meaning an exception to the rule. If you look very closely at all those electron configurations on the periodic table, you will find many of them do not follow the exact trend that I've taught you in determining the electron configuration. So these spaces here, I'm going to put the electron configuration for chromium, what we expect it to be, and then I'm going to put down what the actual electron configuration for chromium is. There's the explanation for why that is, even though before we've done it, but that's fine. I'll let you just keep writing. We'll go back and make sense out of it. So you can go ahead and, if you're done writing this, you can go ahead and do the expected core electron configuration for chromium. That goes back to argon. And actually, because you have your periodic tables right in front of you, you could write down the actual electron configuration for chromium, because the periodic table has the true electron configuration. Has anybody got the electron configuration for chromium, what we'd expect due to its position here? What do you got? Yep, Sarah? 4s2, 3d, oops, 4, right there. Scribble, scribble, scribble. Don't mind that dot. Excellent. And that's using what I've taught you, and that's excellent. That's exactly correct. That's what we would expect. Has anybody located it on the periodic table and found the actual one? Sean, what do you got? Yeah, and I'm going to write it as 4s1 just to put it in line with what we've done, and 3d5. Excellent. And that's what it says on the actual periodic table. So what has happened here? Well, for some reason, one of the electrons in the 4s orbital has been promoted to the 3d orbital. Even though the 3d orbital is of higher energy, it has been moved up for some reason. Now, you might think that this breaks some fundamental law. It would be the Aufbau principle, right? Because the Aufbau principle states, fill the lower energy orbitals first, then move your way up to the higher energy orbitals, and that's what gives us our orbital filling configuration, our orbital filling rules. That's why we fill the 4s first before we fill the 3d, because for some reason the 3d is a little higher energy. Well, it turns out that the energy difference, that energy jump between the 4s and the 3d is quite small. They're really energetically fairly close together. So any little tiny energy gain that can be achieved can result in a promotion. All right, we call this a promotion. When you take an electron that is of lower energy or appears to be of lower energy and you move it to a position of higher energy, we call it a promotion. It's been promoted. It's been moved up. If you take a look at this promotion, it results in the d subshell being half filled. The d orbitals can hold 10 electrons. To half fill the d subshell, you end up with some kind of stability. It becomes more stable. My hypothesis on why the promotion takes place. Even though electrons will pair up, like in the 4s2, they're still all negatively charged. And if given an opportunity energetically, that's energetically favorable, they still would rather repel each other away and fill all individuals in those orbitals. And so there's an energetic gain to filling this all by themselves, having all, individual spots in their own rooms, as opposed to having the pair in the 4s and then having an empty d orbital. All right? So that that empty d orbital is sitting there energetically really close to the 4s, and the repulsion of that 2 electrons in the 4s is enough to promote and spread them all out. All right? Now you'll notice if you move on to the next one, which is manganese, if you take a look at your periodic table, 3d5-4s2, so the next electron goes back into that lower energy level, and that's because promoting doesn't gain you anything anymore. If we've got 4s2, 3d5, and I try to promote one, I'm going to have to pair one up in the d. I'm going to have to stick it in the same room. That's no gain whatsoever. You still have 2 electrons being stuck into the same orbital. You don't gain anything by that. So if you have a d subshell with 4 electrons and there is a full s, it will promote. Take a look down below chromium to molybdenum. All right? On your periodic table, you should have it. You'll notice that the exact same promotion takes place. We have an electron from the 5s being promoted up to half fill that d. So for molybdenum, it says 4d5. Again, we've got 5 in there, and 5s1. The promotion was beneficial. Okay? All right? Yep.
If it was like a 3d3 and a 4s2, would those...
No, the gain isn't there. Let's take a look. All we have to do is move back one. See, all we have to do is move to vanadium. Doesn't happen. It's only the gain to get that half-filled D subshell. 4 to 5. Yep. Yes, that's right. Because you also get a gain by getting a completely filled D subshell. There's a gain somehow for that. And you might be saying, but that's still pairing one up. It's a different type of a gain, but there is an energy gain. So let's take a look at copper then. Copper is the other one. So we're looking again at argon, I believe, because copper's in the same row. And we're looking at 4s2 and 3d9. And if you take a look at copper, you'll notice another promotion takes place. You've got argon, and you've got 4s1, 3d10. Now, my little explanation about separating it out doesn't work there, because you still go from a pair to a pair, right? You still go to spreading it out. Or sorry, you don't get the gain from spreading it out and having it not being paired up, right? But these orbitals are of completely different shapes. There must be some kind of energy benefit. 4s is spherical. The D's are these larger clover leaves. And then that funny one with like the hula hoop in the middle. So there must be something energetically beneficial to taking an electron that's in that spherical orbital and putting it into a D. It must somehow spread that charge out a little bit, just enough to make it beneficial. Yep. Yeah, that's right. But there must be a benefit to that. That's what I'm saying. There's an energetic benefit to that half pairing and all pairing. That's exactly what I'm trying to get across. Do I know exactly what that benefit is? Obviously not. I'm tripping over every second word I'm trying to explain here. But again, in university, I recall they're just saying there's a benefit to that promotion. All right, and I'm attempting to try to, give you something to latch onto. But there must be an energetic benefit in order for the promotion to take place, and it does. And yes, all you guys have to worry about is row, what are we looking at? Row 6 promoting, right? And then row 9 promoting there. Or sorry, row 11 promoting. You're right, in terms of the D, it's 4 in the D, right? And 9 in the D will promote. Now, if you look your way down to the F's, you'll find there's all kinds of weird promotion going on, that they don't follow that rule that we talked about. And that's because a similar type scenario can happen, but then you've got F's and D's promoting, and there's all kinds of mishmash of where the electrons go. And that's because as we get to the bottom of the periodic table, all those energy levels get closer and closer together. And so any little energy benefit from spreading things out will happen, and we've got then all kinds of goofy electron configurations. Again, our electron configuration and our quantum theory is still just a theory. It's still just an idea to explain what we see. It's a pretty good idea, but when we get to lots and lots of electrons, the idea kind of falls apart a little bit, and so we've got exceptions, right? We've got all these little tiny exceptions that we try to explain away. In terms of explaining the chemistry of these guys up here, it works great, and that's really all we're worried about. The chemistry of these guys down here, we don't deal with the chemistry. They're unstable, they're radioactive, they tend to decay and not exist very long, so we don't do a lot of chemistry with those guys down there. Okay. Now, I'm not going to do this example. I was going to have you do the explanation for silver and molybdenum. They're just below it. You know, be aware that those could appear on a test. Any of those four, really. Any of those four, I could say, tell me what the expected is, tell me what the actual is. And there's a handful of practice problems that go with that. Now, to finish off for today, I'm going to do a very quick review of Lewis diagrams and how they kind of work together with our new idea of s orbitals and p orbitals and d orbitals. And then that's it. I've actually got some review because this really is one little chapter that I've quickly gone through, and that's what the quiz on Monday is going to be about. Okay, so just a little review of Lewis structures. Because even though we've learned kind of a new way to think about the atom, energy levels and orbitals and half-filled subshells and all this type of stuff, the Lewis diagram is still a very important way of representing that. And when we start drawing molecules, our starting point is always going to be the Lewis diagram. So we need to be able to think in terms of Lewis diagrams. So a Lewis diagram, as we know it, and to compare it to what you've just learned, is a visual representation of the valence electrons in the s and the p orbitals. The d orbitals, well, in what we're learning in this course, we don't worry about them participating in sharing or bond formation. In reality, they do participate in bonding formations. If you take something called an organometallic chemistry, where you learn about how organic chemicals can interact with metallic chemicals, you will have the d orbitals of things like iron and cobalt, nickel, whatever, any of those biological metals that are important to our body. They will be bonding with carbons and hydrogens and oxygens. They will be bonding with their d orbitals. They will be forming double bonds and triple bonds, just like our non-metals bond. They can bond using their d orbitals, and that's how things like hemoglobin can function and exist the way it is. That iron atom in the center of that hemoglobin complex is being held there by covalent bonds. So you will learn that the metals that we told you only participate in ionic compounds, they can form bonds. And they use their d orbitals to do it. That chemistry is above what we're going to be doing here, okay? So we're only interested when it comes to covalent bonds, s and p orbitals. And that's what a Lewis structure represents, the electrons in the s and p. So if I'm looking at hydrogen, again, I'm going to draw an electron, write an electron configuration here, 1s1, right? And therefore, it's Lewis diagram right there, right? We all know that. And that's what that dot is representing, that electron in that 1s orbital. Okay, handful of examples here. So carbon is helium. Oops, I was going to draw an energy level diagram. Don't want to do that. And my eraser is broke. I've got to fix the eraser. Helium, and now I'm doing electron configurations. 2s2. And what are we at? 2p2? 2p2. And you'll notice I've got 4 electrons there. And so the Lewis diagram for carbon is 1, 2, 3, 4. All right? And we spread them all out. And we'll talk a little more about why they get spread out. You might think, hey, they're paired up in this thing here, and they're paired up in here. Why wouldn't we put them as 2 and 2? I've got to teach you more about something called hybridization theory. We'll talk about that very soon. Okay? So it's just the S and Ps. So oxygen, again, is helium. Again, it's 2s2 and 2p, is it 4? 2p4. And oxygen, all we're doing here is the 6 electrons. 1, 2, 3, 4, 5, 6. And this you can almost make sense of. If we think of the energy level diagram, our energy level diagram will have a pair in the S, and there will be a pair in the P, and then there'll be 2 that are all by themselves. So there's the lone ones there. All right? Oxygen doesn't make sense, because you'd think it should be a pair and pair, and it should be stable. But something happens to that. Sorry, carbon doesn't make sense. All right? The oxygen kind of does. Selenium. So down here, selenium, we're going back to argon. And then I'm going to 4s2. And I'm going to 3d10. And I'm coming across 1, 2, 3, 4. And that is 4p4. 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 And again, we don't care about the 3D subshell. All right? In this case, it's full. It's not going to do any interacting anyway. 1, 2, 3, 4, 5, 6. So selenium looks just like oxygen because there are 6 electrons in the S plus P subshells. Okay? So even though we're dealing with these guys down in here, we can still draw a Lewis diagram. We just ignore these guys in there because they're full and they're stable. They're not going to be interacting with anything anyway. Okay. We are almost there. Beryllium and boron. Yeah, let's talk about those. Last year, we kind of glossed over beryllium and boron. The textbook likes to stick a beryllium in and a boron in every once in a while, which makes me mad, the grade 11 textbook. Because beryllium and boron are special cases.
Morning.
Good morning.
How are you?
I'm good.
Look for Hannah Langstaff.
Right there.
Yeah, that's her.
Yep.
Big trouble.
Yeah, I don't know. I wouldn't believe anything she says, really.
Morning.
So, beryllium, again, it's kind of silly to do our core, but that's the way we've been doing it. 2s2, and that's it. So, in the past, we said everything is eventually going to have an octet, and it's going to have a full outer shell, except for hydrogen, which only needs 2. Beryllium is also an exception. Beryllium's Lewis diagram is literally just 2. There's only 2 electrons in that outer shell. So its bonding is special. We'll be dealing with examples of that. Okay? They're not together, even though you might think they should be together, because something happens to that atom as well. We'll talk about that when we get to hybridization. Boron is the same thing. All right? Boron, 2s2 and 2p1. 2p1, again, there's 3 electrons. 1, 2, 3. So these guys are special cases. And again, we're just taking the S and P electrons and putting them on the diagram. Okay, so essentially I'm at the end of chapter 3 of the textbook. This is what the quiz is going to be on Monday. and it's a, you know, it's not just a little baby quiz, and it's not a full period test. It's one of those in between guys. It's a quest. Gotta love that. What's on there? Energy level diagrams, electron configurations. Oh, quantum numbers. Right? Questions like were on that first worksheet. Is this a valid set of quantum numbers? Tell me the possible quantum numbers if L is equal to this, right? Letter designations, that type of thing. No multiple choice on it, a couple of pages, and it's a couple of the smaller pages, but there's a lot of space because you've got to draw diagrams on there, right? So it's not like it's loaded full of all kinds of stuff.